So, we saw earlier how you can take the ideas behind reinforce with baseline and kind of develop that into an actor critic setting, right. So, there are many variants of actor critic algorithms, but what are the common features of these actor critic methods, right. So, the actor critic methods have two different function approximators, right. The first one is for the policy, right. The first function approximator is for the policy pi, and it has a set of parameters theta, right. So, so far like we have been looking at the policy gradient setting, right. So, we said there are parameters theta which when updated gives you a new policy. So, you have that and you call that as an actor, because that tells you how to behave in the world, right. So, it's an actor network, right. And then you also have what is called the critic, right. It typically, the critic gives you some kind of an estimate of the value function we had, right, and it is parameterized by some set of parameters W. So, this is the standard thing that we will use. Theta means it is the parameters of the actor, W means it is the parameter of the critic or the value function. Okay. So, as we saw earlier, so the critic kind of serves as a baseline, right. So, it is called the critic because basically it is really evaluating how good the policy that you are learning is, right. So, it is actually V hat is a value function of pi theta, right. So, V hat is a value function of pi theta. So, you can think of V hat as evaluating how good the policy is or how good the parameters theta are in some sense, therefore, it is called the critic. Okay. So, the setup is something like this. So, you have an environment and then you have an agent, right, and so you can think of this as the right. This is the agent, right. So, the agent has both a critic which gives you the value function, right, as well as the policy which is the actor, right. So, the critic and the actor are both part of the agent, and as we will see in a bit, both of these are trained using the TD error, right. Both of these are trained using the TD error, right. And as before, so the agent senses the state, right. The agent senses the state and takes an action, and then it goes to the next state as well as get a reward, right. So, that is basically the cycle, right. So, as far as the original model is concerned, it is still there. So, there is an agent interacting with the environment in a closed loop, etc., etc. But with inside the agent, instead of looking at just one Q function or just a policy, you have both a value function as well as a policy pi. So, that is the setting for actor critic methods. Okay. Okay. So, the basic actor critic algorithm works as follows, very similar to the setup that we saw earlier, except that we are making it more simplified now, right. Instead of having all the paraphernalia that we had earlier, we are now making it a simple algorithm, right. So, you have a policy pi theta, right, for the current setting of parameters theta. You take an action A as sampled from pi theta given the current state S, right, and then you receive the following experience, right. So, you have state, action, next state and reward, right. You have state, action, next state, reward, right. And now what you do, you update the value function, right. You update the value function. By that I mean you update the W, right, by using this set of experience, right. The input to the value function approximator is the state S, and the target that you expect from the value function approximator is R plus gamma V hat of S prime, right, because that is the Bellman target, right. So, that is what we have been using so far, right. So, then so that the error that you get will become the TD error, right. So, that is basically what happens here, right. Then you compute the TD error. So, the updation of the W can be done like we talked about earlier, right. It can do this in a batch mode, right. You can do this online, right. You can do this with replay buffers, etc. Okay. So, however you want to do this, but this is the basic setup. The input is state and the output is the desired output is the Bellman target or the TD target, and so you get the TD error as your training signal, right. And for training the actor, right, you explicitly compute the TD error like we saw earlier, right. You explicitly compute the TD error and plug in the TD error into the policy gradient update rule, and then you update the parameters theta, and you keep iterating until you end the episode, and then do this for how many ever episodes you want, right. So, this is a completely incremental way of doing actor-critic updates, okay. And so, like I said earlier, right, the critic can be updated in multiple ways. You are basically looking at minimizing the squared loss, which becomes the square of the TD error, and we have seen all of this already, right. So, we do not have to think about too much. You can go back and look at the value function approximation slides, and the one that we did before DQN, the one we did after DQN, all of these techniques can be used for learning the critic, right. So, you are not limited to using some plain vanilla version. You can even have a critic that is learnt using dueling architectures or whatever. So, whatever is the value function learning methods that you looked at, you can use that for learning the value function here, right. So, there are two kinds of choices you can make, just like we talked about in the Q learning setting, right. So, where you could have one function approximator for each action, or you could have them share the network and just have different heads for different actions, so on and so forth. You could have two networks, one for V hat and one for pi, right. So, all these weights will constitute W and all these weights will constitute theta, right. So, it could be one of those, right. On the other hand, you could also have a shared network design, as we talked about multiple times already. This kind of a shared network sometimes gives you a lot more robust feature learning. So, what happens is about some of the outputs, literally one of the outputs will be for outputting what is the V hat, right. So, that will output V hat of S, right, and the rest of it will give you pi theta, which because it has to give you one output for each action, or some kind of a sample distribution, right. So, you have to have some kind of a mu and sigma, which you then sample from, and so on and so forth. That will be the rest of the outputs will be for the pi, right. And now, the weights that connect to the V hat output, right, will be part of W, right, and the weights that connect to the pi outputs will be part of theta, and every other weight, right, every other weight that you have will be part of both W and theta, and therefore, they will get updated both in line 2 as well as in line 4, okay. So, the shared network will get the weights in the shared part of the network will get updated when you update the W and as well as when you update the theta, okay. So, it is not necessary that W and theta have to be physically distinct set of parameters. You could potentially share them and update them also. That is basically what the shared network design allows you to do, right. So, I am going to now work on introducing this concept of advantage actor critics, right. So, some of you remember the advantage function, we saw that already in the dueling DQN architecture, right. The advantage function is the difference between the Q value and the value function, right. The advantage function is essentially a measure of how much better can you do by doing an action A corresponding to doing the action mentioned by pi, right. So, there could be some action or some distribution over action mentioned by pi. So, instead of sampling according to pi and doing these actions, right, if I deterministically take A in state S, right, how much better than I can I do than pi. So, that is basically what the advantage function is. So, you can mathematically write the advantage function A pi of S comma A as Q pi of S comma A minus V pi of S, right. So, V pi of S is essentially the average over all the Q values, right. So, that is kind of tells you, okay, this is the baseline, and this Q pi SA tells you how much better you are doing than that, right. So, one way of thinking about this Q pi SA minus V pi of S is to think of this as as equal to R plus gamma times V pi of S prime, right. Now, given that I took action A, right. Is it clear? So, from Q pi, if I take action, from state S, if I take action A, then I get a reward R, then I go to the next state S prime, right. That is what we look, that is what we have been thinking about, right. So, this particular reward plus this particular expression, right, R plus gamma V pi S prime is actually a sample of what Q pi S comma A will be, right, because Q pi S comma A basically says I take action A and follow policy pi thereafter. So, this is the follow policy pi thereafter part is captured by the V pi, and taking action A is captured by the sample R and the sample state next state S prime that I am getting, because all of this was sampled by taking action A, right. So, we looked at it already, right. This is how, in fact, if you think about the policy gradient theorem, you had q pi and then we substituted that with this expression, right. First we substituted q pi with the return, right, the return that you get by taking action A and following pi thereafter, and we said the return has a high variance, and we said we will substitute that with R plus gamma v pi of S prime. So, we said that already, right. But now this we know is q pi, and once we add the baseline, we are subtracting v pi. So, putting all of this together, what you have, basically your delta, right, your TD error itself can be thought of as the advantage function. This is the TD error that you get when you are in state S and you take action A, right, and then you compute what the TD error is, right. That part of the TD error, right, not expectation of TD error over all actions you will take according to pi, right, but the TD error that you get by starting in state S, taking action A and using v pi thereafter, right. That TD error is essentially the advantage function. So, whenever I use the form that we had earlier, right. So, let me go back. So, whenever I use this form, right, given by this, right. So, where I take R plus this R and S prime are sampled by taking action A, right. So, whenever I have this expression, I am actually using the advantage function. This is actually the advantage function of S comma A, that is what I am using here, and therefore, sometimes this kind of actor-critic method where I am actually using the TD error in the policy gradient update is known as a advantage actor-critic methods. Okay. So, that is basically where we get the idea of something called advantage actor-critic. Okay. So, that is the advantage actor-critic approach, right. So, we are going to look at a slightly more subtle concept than the advantage actor-critic. We are going to put one more A in front of it. It is called A3C. The algorithm A3C is one of the most popular algorithms, right. In recent times, people have been using A3C quite a bit, and the other one which we will see later is the DDPG. So, this is called asynchronous advantage actor-critic algorithm, right. So, the idea behind the asynchronous is that, hey, I have a policy pi, right. Sorry. So, I have a policy pi theta, right. I have a policy pi theta, right, and what I want to do with pi theta is generate many trajectories with pi theta, right. Then only I get a better estimate of the gradient of the performance with respect to theta, right. If I just take one transition, that is a single point I estimate. If I take many transitions, many trajectories using pi theta, then I get a much more robust estimate of what the gradient is, right. More samples, better estimate, that we know. So, one of the ways that we can take advantage of recent modern advances in architecture is to say that, hey, instead of generating these many episodes in sequence, I could do them in parallel, right. I could have n copies of the agent, right. I could have n copies of the agent, each of which is actually selecting actions according to pi theta, but they are starting in different points in the state space and then generating trajectories. So, that way I am getting more experience in the same time, because they are all running in parallel, right, because they have multiple processors and running in parallel. So, I am getting more experience in the same time, so that I can learn much faster. So, that is basically the idea. So, I am going to have n different agents, right, and I am going to have a set of global parameters, right. There will be a global theta and a global w, right. So, there are a set of parameters theta and w for the actor and critic that is maintained in a central store, right. You could call that the parameter server. So, that maintains the theta and w, and each of these agents is going to take a copy of the theta and w, run some trajectories on the world, right, and get these experiences, compute the gradient for theta and w, and send them back to the central server so that the parameters can be updated. So, that is roughly the idea. So, let us see how that is done. So, this is basically for each of these agents, right. So, each of these agents, what do they do, right. The central server basically is going to take up all the updates, each agent sends it, and then changes the weights both of theta and w, and then whenever an agent asks for theta and w, it will send whatever is the latest copy of theta and w that it has. Okay, so that's basically what it is. So you are talking about this each actor thread, right? So each of these agents is potentially just an actor. Right? They are not updating any parameters. Right? They are just actors, and they don't even have to use the critic, because once you have trained a policy, right, using actor-critic, when I want to behave in the world, all I need is the policy. I don't need the critic anymore. I need the critic only when I am learning, right? If I am not learning, then I need only the actor. So that's a nice thing about it. Right? So the actor, as you know, learns a simple policy, and when you are actually using the policy learned by the actor-critic, you only need the actor. You don't need the critic. So each of these threads, the agents that we talk, are called actor threads, right? Because they don't actually update the parameters. They are just executing the policy that has been learned, right? So let's see what they do. So that is the set of theta and w, which is global, right? And then you make a copy of that, right? So you take theta and w, make a copy, right? So theta prime and w prime are the copies that you make for the current thread, right, or current actor, right? So the current agent, and then you start, right? You get the current state, right? Perform action A according to the policy given by theta prime, right? You sample a state, get the next the reward and next state. So I mean, normally in our things we would have used RT plus 1, but in this paper they used RT, right? What they mean is RT plus 1 in our terminology. So you are starting in state ST, perform action AT, then you get RT plus 1 and ST plus 1. Okay, so this should be RT plus 1, and you get the new state, and then you keep going, right, until you reach a terminal state or until you time out, right. So you know by now you would have been running experiments, you know that sometimes you just have to stop the trajectory, right, you just can't get it run forever. So either you time out or you come to the terminal state, right. So basically this is what you would call a gather experience phase. So this is an initialization. Now you have gathered the experience. Now that you have gathered all this experience, you can use that to compute the gradient, right. So how will you do that? So basically remember what you have to do. So you have to update, right? You have to update theta prime using the policy gradient theorem, right? So you take the gradient of log pi with respect to theta prime, right? And then you take r minus VSI. So this is basically your TD error, right? So in fact, what you do here is a little cleverer. The TD error he used is basically the return from that point till the end, right? Whatever is time t, you take the actual return. So this is not the one step TD error. This is like the n step TD error that he used. It's a small efficiency that they did in the algorithm, but you can also implement A3C with a one step TD error. It will work fine, right? But these guys try to be more clever and push the boundary, so they use the n step TD error, right? This is like the n step error. That is what this R is computing. Right? You can see that it accumulates the return, right? So it basically uses the n step TD error until going all the way till the end of the episode, right? And likewise, this is for the actor, right? And for the critic, basically it does the same thing, right? It takes the n step TD error, takes the squared error, right? And then takes a derivative and uses that for updating the critic, right? So one thing you have to note here is that both the theta prime and w prime are actually not changed. Theta prime and w prime are not changed. I am just computing the gradient and then keep adding it up. It's like a batch mode version, right? So where in batch mode you don't change it for every sample, right? You take all the samples in the batch, you run it through, right, and then compute the gradient for each and every sample and take all the changes, accumulate them, and make one change to the weights at the end of the batch, right? So like that, what you are doing here is for this episode that you generated, right? For this episode that you generated here, right, in the green box, right? The episode is generated there. You accumulate the gradient for the entire episode. So that is what you are doing here, right? And after that, what you do is you send back the total update to the main server, right? So you don't update theta prime and w prime. You update theta and w. That means it has to be done in the parameter server, so it has to go back to the global setting, right? Go back and then update it. I don't care what the other threads are doing. As soon as I finish my set of transitions, or as soon as I finish computing for my episode, I'll go back and change the parameters in the main server. Okay. So now as long as these each agent is not, it's like one particular agent is not delayed for an indefinite amount of time, as long as these are reasonably going one after the other, right, these asynchronous updates will work fine, right. So I am not accumulating all the gradients updates in one place and then doing it, I am just doing it as and when the updates are available. So what is the problem with doing it as and when the updates are available? So remember that I am copying my theta and w from some setting, right. So let us say that this is my main server, right, this is agent 1, right, this is agent 2, right. So at some time t, I will copy over to agent 1, right, I will copy the weights over to agent 1. So at this point let us call it theta 1 and w1, that is being copied, and then I copy again to agent 2, again let us say this is theta 1 and w1, that is being copied to agent 2. Now agent 1 is doing its experiments and agent 2 is doing its experiments, and somehow agent 2's episode ends quickly, right, maybe it hits a terminal state much more quickly because it started from some convenient point. So it will go back here, now it will update it, now this has become theta 2 and w2, right, and now agent 1 finishes and it will update it, now this will become theta 3 and w3, but the problem is agent 1 is computed the gradient at theta 1 and w1, it computed the gradient when the weights were theta 1 and w1, but when it is updating the weights have already moved to theta 2 and w2, right, they are no longer at theta 1 and w1, but I am computing the gradient at theta 1 and w1. So as long as the change from theta 1 to theta 2 is small, right, as long as this change is small, the magnitude of the change from theta 1 to theta 2 and w1 to w2 is small, this gradient that I am using here will be okay. But if this change is very large, right, then basically I am computing a gradient at some point in the state space, right, I am using it to update the values at some other point in this in the weight space. So that basically becomes an issue. Okay, so we'll have to think about that. So asynchronous works fine as long as each of these agents are not too extraordinarily delayed. If they are too delayed, then they might actually use a wrong gradient. Okay, so that's one thing that you have to think about. But otherwise, A3C works great as long as you're able to implement this kind of asynchronous threading, then it works fine, right. So one advantage that you should look at from A3C is the fact that each of these agents, right, agent 1, agent 2 and so on and so forth, each of this agent is running independent of the other, right. So the kind of sequence of states and actions it will see will be independent of the other agent, right. They are starting in different points of the state space, they are exploring different parts of the state, and therefore your correlated updates problem that you had with the DQN, right, for which you had to use a replay memory. So for correlated updates we had to use a replay memory. So that replay memory problem or replay buffer problem doesn't exist here, right. The correlated updates don't exist here, because when thread 1 makes an update followed by thread 2 making an update at the same more or less the same point, they will be using very different sets of experiences, and therefore the gradient will not get completely messed up. Remember, the problem with the correlated updates was you will be using only one side of the input space, right, for computing the gradient, and therefore your gradient could be severely biased, right. So you might lead to wrong convergence, but now that's not a problem anymore. And so with Actor-Critic updates, you don't really have to use a replay buffer. You could, because you want to make better use of the experiences, but you don't have to use a replay buffer, right. And replaying, I mean updating the actor with the replay buffer is all fine. Updating the critic with the replay buffer becomes a little bit more challenging, but we will not get into that now. So but for the time being, just assume that A3C does not use a replay buffer, because the correlated updates problem doesn't exist, right. So what about the free target network, right? Does A3C need to use a free target network? Not really, because if you think about it, A3C is not even using a bootstrap, right, for updating, right. It's actually using the n step return, but all the way to the end, right. It's not actually bootstrapping. Therefore, we can, as long as your episodes terminate, right, you don't have to worry about free target network. But if your episodes are non-terminal, I mean if you are actually cutting it short, right, then you will be using bootstrapping, right. You will be using bootstrapping, but that's okay, because you're bootstrapping from W prime, right, not from W. So just like a free target network. So you get the free target network effect for free when you're using Actor-Critic. So you don't have to think about both of those DQN things explicitly when you're doing Actor-Critic, But like I said, there is this problem when you are doing this asynchronous updates, where if one agent gets delayed, it might be using a completely wrong estimate of the gradient, right. So, one way to get around that is to do synchronous advantage actor-critic, or which is sometimes called as just A to C, right. So, you do not have to, advantage actor-critic can be implemented as a single agent application also. You do not have to do this in parallel, but doing it in parallel helps because you are able to do more experience, right. So, you are able to gather more experience quickly. So, doing it in parallel helps, but it is not needed, right. So, having said that, what happens if I want to train in parallel, but I do not want to get into the problems I have with asynchronous updates, right. So, what I do in such a case is that I include what is called as a coordinator. So, what is the role of the coordinator, right. So, if you remember, I told you this, right, in asynchronous, so from each thread is going to sample independently from the central repository and update independently, right. They are not going to wait for each other to complete, right. But in synchronous actor-critic, what you are going to do is that you will have the central setting for theta and w, and each of these, right, threads, each of these actors will get theta and w from the central server, and then so the coordinator will make sure that every thread waits for the other threads to finish. You can see here, right. So, all of these threads are waiting for the other threads to finish. So, once all the threads finish, the coordinator will get all the delta w's and delta thetas from these threads, combine everything and make one update to theta w, right. So, theta and w will get updated here, right, and then again you copy it back to the threads and have them run, right. So, this is basically kind of you get the advantage of running things in parallel, so you can generate more experience, but then you stop things and make sure that the updates are all synchronized, so that the gradients that you are computing are the true gradients of the weights, right. So, with A3C you might be computing gradients at some theta, but applying the weights, the modifications at some theta prime, right. But that does not happen with A to C. A to C you will always compute the right gradients and you will apply it at the point where you computed the gradient. Okay. So, what is the problem with A to C? Well, if one of the threads gets delayed or one of the thread crashes or whatever, right. So, all the other threads will be waiting for that one thread to finish, right. So, that is the problem, right. So, you are kind of losing the advantage of doing things in parallel, because you are now waiting for everybody to finish. So, sometimes these threads could just be idling while they could have happily just done the parameter updates and gone ahead, right, in the asynchronous case. So, there are pros and cons to both ways of doing this, and quite often people do A to C, right. For many of the toy applications and simple installations that you will be working on, most likely do A to C with one actor, right, one actor agent, right? Not multiple agents. But if you want to get more efficient computation, you have to do this with multiple agents. So, that is basically the advantage actor-critic part, right. So, I have one final note to make about the basic actor-critic setup when we are using function approximation, right. So, we are looking at function approximation various forms, right. So, we have looked at the Monte Carlo version of the target, we looked at the TD version of the target, we looked at advantage actor-critic, we looked at just using the value function, etc., etc. There are many ways that we are looking at it. All of these are essentially some kind of an approximation of what Q hat should be, right. If you think about the policy gradient theorem, it has this Q in there, and what we have done is we have taken out the Q and replace it with some approximation which we call Q hat, right. Now, the problem by introducing Q hat is that it is going to have some kind of a bias, right, because I am as I using weights and I am using some kind of a approximation. So, I will be introducing some error into the estimate of the gradient. Now, if my W network, right, the Q network or the V network that I am choosing, right, is such that I am not able to represent the value function of the policy pi theta accurately, right. If I am not at all able to represent the value function pi theta accurately using my W network, then my estimate of the gradient will be very, very wrong. Get that? Suppose there is some value function that I have to represent for pi theta. Remember my Q hat, if you remember that, right? I said the V hat and Q hat are essentially the value functions of pi theta, right? I am trying to get to pi theta. Now, what will happen is my pi theta, right, I'm sorry, the W function might not be able to represent the V pi theta accurately at all, right. If it's off by a huge margin, right, then obviously my gradient estimates are going to be wrong, right. So, my policy gradient theorem will no longer be guaranteed to converge, right. So, what people have come up with these two conditions, right, to show that this can actually work, the policy gradient theorem can work with the function approximator for the Q function, provided these two conditions are satisfied, and these conditions together are called as a compatible parameterization condition. So, we have to call this as a compatible parameterization, right. So, the second condition is easy to explain first. I will go with the second condition. So, you have to choose a W such that it minimizes the following squared error. So, Q pi theta SA is a true Q function that you want to plug in into your policy gradient theorem, right. Q pi theta SA is a true Q function you want to plug into the policy gradient theorem, and Q hat is the approximation that you have, right. So, the W should be chosen in such a way that it minimizes this expression, right. So, this is basically the expectation where I am sampling the states according to my steady state distribution, right. That basically means I have to take actions according to pi theta, right, and I am sampling the actions according to pi theta. We looked at this, right. We had two expectations, we kind of reduced it to a single expectation when we did the simplification of the policy gradient theorem. So, basically what it says is, hey, if you take the expected squared error according to the distribution that we are using in the policy gradient theorem, then W should be chosen such that that expected squared error is minimized. Okay, that is basically what it is. So, W minimizes the mean squared error, right. So, that is basically it, right? That is great. Now, but the challenge is slightly different, right. This is obviously the common sense thing. I want to pick the W that gives me the least error, great. But what if the least error is so big that it is no longer useful? I have the W that gives me the least error for my Q hat, right. But if the error is big, it is not useful, then what we do is, hey, look, what we really need to figure out is a way to have this W, right, so that, right, when I project that characteristic eligibility along the direction of the W, right, I get something along the direction of the Q function. So, this is a pretty strong condition, right, and people have been struggling to figure out what is the right way to select these features, right. So, this is basically says that my Q hat has to be linear in my characteristic eligibility given the W that I have, right. So, that is basically what it says. Basically, it says that my function approximation has to be a linear function approximator where the features phi are basically given by the characteristic eligibility. Right. So, that is a strong condition for any arbitrary function approximation to satisfy. Of course, the linear function approximator will obviously satisfy that. So, we are happy as long as this expression on the right is in the correct direction of the Q function. It does not have to be exactly matching the Q function, but as long as it is some kind of a scaled version or within some bound of the Q hat direction, we are happy. So, that is but for the policy gradient theorem to work perfectly, right, you need this condition to be satisfied, right. But given all this complex parameterization that we use nowadays, right, with the Q learning and all that, with the deep neural networks and all that, nobody can even verify whether these conditions are satisfied, and we go ahead and implement things anyway. Mostly they work, but you do not have any theoretical guarantees. Okay. So, that is about compatible parameterization. I had a quick note that I wanted to make about, I am just going back a few slides so that I can talk about this particular point, right. So, there are two sets of parameters we have, right. So, we have alpha theta, which is what we use for updating the theta, that is a step size for updating theta, which is the actor, and alpha W, which is a step size that we use for updating the critic, right. So, alpha W is the step size for the critic, alpha theta is the step size for the actor. Okay. So, remember that we want the critic, right, to learn V pi theta, right. We want the critic to learn V pi theta. So, that means that we have to make more updates to the critic for a fixed theta, so that the critic can move towards V of pi theta, right. If we keep changing theta much more frequently than we change the V, right. So, if we change theta, if we change the policy pi more frequently than we change V, then V will not be able to converge to V pi, right. So, V has to change faster than pi. That means that your alpha W's have to be larger than alpha theta, so that you move faster towards the pi theta, right. So, it is not very much larger, but at least so that you are learning the value function changes faster than the policy will change, so that this convergence can happen. So, sometimes actor-critic methods are also called as 2 time scale algorithms, because alpha theta determines the speed at which the policy is changing, alpha W determines the speed at which the value function is changing, and these are not the same. Therefore, they are called as 2 time scale algorithms, and then you have to take that into account when you do all kinds of analysis of these. But in practice, right, when you are trying to write these actor-critic algorithms for convergence, make sure that your critic update rates are faster than the actor update rates, and you will see a big difference when you do these things in practice. If you keep the update rates the same, then you will actually find the learning being a little bit more unstable. Okay. Because this kind of appears in all kinds of places, right. So, even here when we talk about the advantage actor-critic, we do not explicitly do that here, but then we have theta and W. When I update my theta using d theta and W using dW, I have to make sure that the W update is faster than the theta update. Okay. So, that is something to keep in mind.